talk of this morning. So if you'd like to take your seats. Second talk is going to be given by Charles Bordenave, Load Optimization in a Planar.
Thank you very much for the introduction. First of all, I want to thank the organizer for having organized such a beautiful meeting and for giving me the opportunity to speak about some of my work in this field. Even if I've not worked quite recently on spatial networks, I might talk. What? Speak up? Okay.
My microphone closer.
Okay. I can put it here maybe. Is it better now or not? Okay. Okay, I will speak louder. So I will try to speak about two different loosely related topics. The first one, I have already talked about it a couple of times, so maybe some of you have heard about it. It's a joint work with Gianluca Torrisi, who is in Rome. So it's a very simple question where you take this shape, a triangle, with you put 3 bins, and you drop endpoints in this triangle, and you want to allocate each point to 1 bin. Okay, so the reason why we have chosen the hexagonal network as such triangle, this is because this is the fundamental domain of an hexagonal network. So if I could have also made the same kind of analysis on a more complicated hexagonal network. I will come to that after. So as I was saying, so each object has to be allocated to one of the 3 bins, and the cost will depend on its position. Okay, so the cost to allocate an object located at position x will be to bin 1 will be c of x. Okay, so the cost to allocate this bin here to bin 1 is a function c of x. Now the cost to allocate bin here to bin 2, this object to the bin 2 will be the same cost as allocating this object if this object was rotated by an angle of 2 pi over 3, so here. Okay, so it means that the cost of allocate an object to bin 2 is c2 of x, which is just c of j2 of x. Okay, and similarly, the cost to allocate an object x to bin 3 is obtained by a proper rotation. So just to keep in mind. So this is bin 1, bin 2, bin 3. And so the cost to allocate an object to bin 1, when I want to allocate it to bin 2, it is the same as allocating this point as if it were here. Okay? No, sorry. As if it were, yes, here. Okay.
Only the angles matter.
Sorry.
Only the angle.
Sorry. To which you allocate your point x to b1, and then you put the symmetrical point in another place, and with which node you allocate it.
It has not done anything.
I've not done. I just defining the cost function. I just say that the cost to allocate a point located at x to a bin.
You have a line between x and b1, and have you another line between another x and something else or not?
I'm not sure I get what you say.
Cost is rotation invariant, that's all.
Yes, I just say that the cost is invariant by a rotation of angle pi over 3. Okay, so then you want to allocate your points effectively to the bin, and so you can encode this into a matrix such that the term of the matrix will be 0 or 1 depending on whether or not point K is allocated to bin L, the sum up to 1, okay, so, and the load that we will be interested in is to maximize the cost that for a given allocation will be the max over all loads of bins of the sum of the cost of the objects which have been allocated to these bins, to this bin, okay? So we take the maximum of the three of it. And of course, the one which is of interest for us is the allocation which minimizes. So rho n. So just before giving two examples, so the first example would be, for example, take C of x as being 2 times the distance between x and b1. So it will be the time to get from b1 at unit speed to x and come back. Okay? So then rho n will be the minimal time to pick up all objects individually. If you had 3. So more closer to this, so the main example probably is to take an inverse signal to noise ratio as a cost. Okay? So for example, typically of this type. And then rho n can be interpreted as a minimal time to send 1 bit of information to all users, assuming that the base stations are constantly emitting, more or less. Okay. So there is also, so I have not made any assumption on the cost C of x, but when we look at the example I have in mind, so what we will assume is that if the distance from x to b, if x is closer to b1 than to b2 or b3, then the cost will be lower. Okay? So then there is also an allocation policy which is quite simple. It's just I allocate bin point K to bin L if it is in this region. So in the Voronoi cell associated to bin 1, bin 2, and bin 3. So I allocate each point to its less costly bin. So it gives me another load, rho bar n, which is of course larger than rho n. And the question is how close it is. So it's in fact of course very close, because it's very easy to see. So if we call gamma, so now the points, just to recall you the model, so you have n IID points in this triangle of unit area. The cost function satisfies this invariance by rotation, and they are, and also the fact that if I am close, if x is closer to the cost is, if x is closest to b1, then the cost is less to any other bin too. So if I call gamma the integral over this Voronoi region T1 of C of the cost, it's very easy to see that almost surely the limits of rho n and rho bar n divided by n converge to gamma. Okay, so we will just check that on the next slide. So it just means that at the first order, the optimal and the suboptimal loads do the same. Okay, so it's quite easy because if you call from the law of large number, okay, if you just count the sum of the weights of the points which are in a given cell, T1 to T2 or T3, okay, of CL of x, it has to converge to gamma. Okay, and then you have that. So rho bar n is a maximum of 3 terms which converge to gamma, so it converges to gamma. Rho bar n is larger than rho n, and rho n, due to the geometric condition on the cost, has to be larger than the average over all the costs where you allocate point xk to bin TL. If you take the average and not the maximum, rho n has to be larger than that. Okay. This is just due to this condition. the fact that when you are closer, the cost is smaller. Okay, so now we can take make one more step. So we will look at the central limit theorem for this problem. So we will need another assumption that the cost is invariant. The cost here and the cost here are the same. Okay? So this is this assumption, so it's a new geometric assumption, and also that we assume that the cost function C is Lipschitz in the neighborhood of the boundary of the Voronoi cells. Okay, and we will call sigma square the integral of the square of the cost. So then we can prove that rho n minus gamma n, so the asymptotic load renormalized by square root of n, converge to a Gaussian random variable with variance sigma square divided by 3 minus gamma 2. And okay, there is also a central limit theorem for rho bar n, but I just write down the central limit. If you look at rho bar n minus rho n, you divide the difference by square root of n, and it converges to the difference between the max of 3 independent random variables with variance sigma square minus the average. And you can also prove that you can integrate this weak convergence. It's uniformly integrable, and you get so that if delta is the expectation of the max of 3 random variables, that the expectation of the optimal load is scales like n gamma plus something which is little o of square root of n, but the scale, if you take the expectation of the suboptimal load, rho bar n, it scales like n gamma plus delta square root of n plus something. So it means that the two loads, the optimal load and the suboptimal load, they are asymptotically equivalent at scale n, but not at scale square root of n. The next step, so the way you improve your performance by taking the best possible allocation policy is just by a square root of n factor. Okay, so I will just explain in a couple of slides how you do that. So if you define so mu n, you look at the empirical measure of your points in your triangle. You subtract L is the Lebesgue measure on my triangle. You blow this by square root of n, and you call this sine measure Wn. So rho bar n can be expressed minus n gamma divided by square root of n can just be expressed as the maximum of the integral of the cost on each cell of the cost CL of this measure. Okay, so and then as you know, this measure Wn, okay, will converge to the standard Brownian bridge. So this is a centered Gaussian process, which is indexed, which is parameterized by all L2 function on the triangle with this covariance. So L is again the Lebesgue measure, so it's the integral of fg minus integral of f integral of g. And by the central limit theorem, rho bar n minus n gamma divided by square root of n will converge to this weakly to this random variable.
So rho bar is the optimal.
Suboptimal. So we'll see that there is another one for.
So what is rho n again?
So rho bar n is a cost which minimize among all allocation policy the maximum of the sum of the which minimize the maximum of the load in each bin. And rho bar n is just allocation where you allocate each point to its less costly bin. So rho bar n is very easy to analyze. So it was just, so if you want to do so it's the same thing. But as I pointed out earlier, the fact that rho n is rho n is larger than 1/3 of the sum of the costs in each cell. When you renormalize things, it implies that rho n minus n gamma divided by square root of n is larger than this. Okay, so in fact we will prove that it is very close to that, and it's close enough that it converges weakly to 1/3. We want to prove that rho n minus n gamma divided by square root of n is very close to that. So we need an inequality in the other sense, and I explained that there exists an allocation matrix, which is not the optimal one because it's difficult to know how to build explicitly the optimal allocation. Of course, we will prove that there is an allocation matrix such that the load associated to this allocation renormalized is less than what we want to show it's closed, plus a term which is vanishing as n goes to infinity with overwhelmingly high probability. And then from that we will deduce that I did not wrote it, but we can deduce this, okay? Because G is just the mean and the variance of 1/3 of that when you replace W n by W the Brownian bridge. Okay, so we need to construct an allocation matrix which satisfies this nice property. It's not very, there is a natural choice to do it, so we will do it by iteration. Okay, so we start with we will find a new tessellation of the triangle. Okay, so the joint union of sets which covers T, such that, and the allocation will be geographic. So it will just be, I will associate bin K, node K to bin L if xk is in the cell CL. Okay, so it's iterative. I start with CL as being TL, so just the Voronoi cells. And then I look at the heavier cells, so for example this one, and I look at the less loaded cell, for example this one. And I move the boundary so that to take a new one, a single node, new point. Okay, so then this one is its load has been reduced, and the load of the minimal has been increased. And you stop until the difference between the max and the min is within a range of 2 times the maximum of C on the triangle. And you can prove that this allocation satisfies this property. I'm explaining in one slide. So it's you allow some kind of bracing of your cells, and so the heuristic is like that. So due to the central limit theorem, the load in each cell is within square root of n from each other. Okay. So if you want to balance the load or the number of points in each cell, you have to move the boundary to get roughly square root of n points. So you have to move the boundary of orders 1 over square root of n, so that you will have n times 1 over square root of n points. Okay. So you need to move your boundary by order 1 over square root of n. But now, what will be the increase in the cost? Okay, because you will have to, this point which was allocated here will be finally allocated here. Okay, but since it's within distance square root of n, okay, you want to compare the cost here with the cost there. That's why there is a, you want to compare the allocation to allocate this point here and this point here. It's the same as looking at the difference of the cost function between this point and this point. And since we have assumed it's Lipschitz, the cost will be modified by roughly the distance, so 1 over square root of n. And since we have square root of n points, it will be times square root of n times 1 over square root of n, so it's supposed to be of order 1. So it means that this result is without this extra term. We should maybe prove that there is some random variable such that this allocation matrix is less than this cost plus some constant, some variable term. So, but we want to do it with a high probability. It will be less than that, so it's enough. Okay, so and then you can also do a large deviation principle. So we call you a large deviation principle is you want to try to compute the asymptotic probability of very rare events, so in on a log scale, and for example, you want to compute the probability that that rho n over n is larger than 2 times its average. Okay, and it can be formalized by you are looking for a rate function j, which is called a rate function, such that over all Borel sets B, so 1 over n times the logarithm that the load is in B, its limit is larger than the infimum of the j of y over all y in the interior of B, and in lim sup is less than the of j over all y in the bounds on the closure of B. Okay, so if you we will see that there is also a large deviation principle, which is very easy in this model. So if you take lambda of theta as being the log of the of the Laplace transform of the cost, so log of 3 times the integral over the Voronoi cell of exponential of theta c of x dx. Okay, and lambda bar, it's the same, but instead of putting the third, you put 1 here, so it's just the integral of theta 1 plus 2 over 3. You define the Fenchel-Legendre transform as being the lambda star and lambda bar star as being the sup of theta y minus lambda of theta, and similarly from lambda bar. Okay, if you have never seen large deviation.
Sorry, what's the 2/3? Is it 2/3 times the cost of assigning it to the furthest point or something?
What's the 2/3?
Yeah, why 2/3? Is there a C implicit in that, or no?
No, it's 2/3. 2/3 is the area of the 2 other cells. That's where it comes from. But so we need to make, we don't need the assumption due to for the CLT, but we need that the level sets are of Lebesgue measure 0. But C is now continuous, and it satisfies that 2 assumptions, that the cost, so this is the origin, the lower cost in the cell will be here, the heavier cost in the cell will be here, okay? And if I could put all points in the same spot, the worst case will be to put all points here. So this is these 2 assumptions. And then with this assumption, we have a large deviation principle for rho n over n with rate function for g of y for rho n, and for the suboptimal a rate function g bar. So what is interesting is if you plot them together, I mean it's a figure, it's not a real plot, but they have the rate function are the same. So gamma is the average. So the rate function has to be 0 at gamma. So the rate function is the same for the suboptimal and the optimal one. So the optimal and the suboptimal one, the rate function are the same for the low load. So when you are below the average, but the rate function are different when you are above gamma. So it means that the probability of an extraordinary low load is the same for the optimal and the suboptimal, but the probability of an extraordinary high load is significantly smaller for the optimal load. Okay, so it's in fact, while all these results are very simple, this is because the rho n, so the optimal load, is the same in terms of law of large numbers, central limit theorem, or large deviation principle as this random variable, which is much simpler, which is just the average over all cells of the cost of allocating the cell, the point in X to a cell to this cell. Okay. So, but it's we have that this row check n is less than rho m, but what we can prove is that at any scale, at the level of central limit theorem or large deviation principle, they behave exactly the same. So it means that rho n, the optimal load, do as if he can, the optimal load manage to average out the cell loads, but rho bar n, the suboptimal, is just controlled by the maximum. So that's where the difference comes from, and if you can compute the rate function for the large deviation of this, which is very simple, you will find exactly what I'm saying. So, but this is not, this just to prove the large deviation result, just an idea. So the first thing is very natural, is just to look at soft allocation. So you allow a point k to be splitted into among the three nodes, among the three bins. Okay, so now the matrix allocation matrix is not 0, 1 matrix, but a matrix with entries between 0 and 1. Okay, so you can split points to. So now you define the minimal load associated to this on this new set. Okay, of course, this load is less than the optimal load because you allow more, you have more freedom, but you are very close to it. Okay, this is very standard. So the only thing to do is to find a large deviation principle for this one. And the reason that why it's easier to look at this one, rho tilde, it's because you can write it as a continuous function of the empirical measure. So to be more precise, if you define phi of three measures, alpha 1, alpha 2, alpha 3, as being the maximum over all cells of the cost CL times alpha L of dx. Okay? So you can write that you can see that rho tilde, so the optimal soft allocation cost, will be a function of the empirical measure, where phi of alpha is just the infimum over all measures. All the way you can split this measure into three measures of the cost. So you can prove that this mapping is continuous for the topology of weak convergence, and then if you open a book in large deviation, you can apply Sanoff's theorem and the contraction principle to get the rate function of your problem. But that's now where the difficulty comes in, because so you have the rate function is equal to the entropy with respect to the Lebesgue measure of the infimum over all measures of the entropy of the measure alpha with respect to the Lebesgue measure, where the infimum is over all measure alpha with function with value or such that phi of alpha is equal to y. Okay, so if you write it in terms of the splitted three measures, you can write it as a sum of the entropy of the sum of the three measures with respect to Lebesgue measure, such that the sum of the three measures is a probability measure, and it is the optimal splitting of their sum, and it's equal, and their load is equal to y. So the problem is that this is a non-convex variational problem. So there is no tools to solve this. But here, due to the symmetry, it's quite easy to solve it once you notice the following. That instead, so this is the non-convex optimization problem you want to solve. So the idea is just to take the infimum of a larger set, which will be defined by linear constraints, so linear programming. Then you can solve this the infimum of the larger set, and then at the end, if you show that the infimum over the larger set is reached at a point which is also in the smaller set, you have solved your problem. Okay, so, and the larger set that we consider is just we notice that for a function to be optimally split, it has to be a probability measure. So the sum of the function has to be a probability measure. Okay, and also the load in each cell is a load. The integral of the load for C1 and the load of C2 and the load of C3 has to be equal. And then, so this is just linear constraints, and you can explicitly solve this problem. And you can prove when y is in some range that the minimizer is in this set. And that's why we have to include the geometric assumption, or because it cannot work, it does not work with all y. Okay, so I just want to, so you could do the same thing where there is a complete symmetry. So if you look at an hexagonal, a finite hexagonal network in a torus, all the symmetry will be preserved and it will work. It should, I've not done it, but maybe for if the model is of interest for wireless communication, it will be more interesting to add for the cost function to add an IID random variable, which will be think about as fading. And then you can try to see is it possible to say something in terms of the central limit theorem for asymmetric networks or things like that. I don't know how to do. So now I want to move to another part, which is an ongoing joint work with Frank Barth, who is in my university in Toulouse. It's about a loosely related problem, but again, the link would be the following. Take endpoint in some domain, like your triangle, and take another set of endpoints that you think about as bins in the same domain. And assume that the number of points in the number of bins, m, is equal to b times n, where b is some integer. Okay, so you think that each bin has b slots, and you want to allocate all your points to a bin. Okay, and so it's an allocation. It's a map from 1 to n to 1 to m, from points to bins, and you want that the number of points which have been allocated to bins j is equal to b. And then if you are since you are in RD, you can look at the allocation which minimize the sum of the lengths of the distance from point to bin power p, where p is some positive number. Yes, sorry. It's n. It's reversed. M is equal to b minus 1 n. Thank you, Sergey. Okay, so there is a very famous algorithm to compute this kind of thing, which is called the Hungarian algorithm. And if you can look at what it look like when you take 400 points. So the blue points are ID uniform in the unit square. The red points are also ID uniform in the red square, but there are only 1/10 of them. And you take p equal to 1, and it looks like that.
Again, what the function is.
You just minimize over all allocation of the sum of the lengths from your point and the bin, the distance from the point and the bin it is allocated to power p.
Obviously being very different, but why are you not allocating every point to the closest bin?
Each bin has.
Is one.
You have only b slots for each. That's where.
So when m is equal to n, this is minimal matching.
Yes. So when m is equal to n, this is just the minimal matching. it looks like that in dimension 2. Yes, Yuval Perez has spent a lot of work recently on this problem. So, of course, so this is for p equal to 1, so the edges cannot, due to triangle inequality, do not overlap. And if you take, for example, p to be 0.5, the geometry is completely different. And okay. So I'm not going to say this is an ongoing work, and I don't have many smart things to say about this model, but I want to generalize this this bipartite structure to sequence where the bins, where you have two sequences of points, and they have some not necessarily each point wants to be connected to, let's say, each point from the first set wants to be connected to k points from the red set, and each point from the red set wants to be connected to l points from the blue set. Things like that. So, and you could also think of k and l as being random variables. So I want to define a kind of bipartite configuration model in space. So first of all, so I take it's called a graphic sequence. So it's a set of integers, a1 to an, and b a set of integers, b1 to bm. We call them graphic if there exists a bipartite graph whose degree sequence is exactly the a's and the b's. Okay, so and bipartite means all red points are connected to blue points, and blue points are connected to red points. Okay, and you are not allowed to have loops or multiple not loops but multiple edges. Of course, the necessary condition is that the sum of the lengths of the red points of the degrees of the red points has to be equal to the sum of the degrees of the blue points. And if you want to look at the sufficient condition, it's known for a long time by it's a paper by Erdos and Galay in 60. So now to reformulate the problem, imagine that you have points, n points in your domain omega. You have y points in your domain omega, so blue and red, for example. You have some degree sequence that you want x1 to have degree a1, xn to have degree an, and so on, and the same for y, for the y's. And you assume that the sequence is graphic, so there is a bipartite graph which matches them. And you want to look at the graph which minimize the sum of the distance over p. So the minimum is over all bipartite graphs whose degree sequence is AB. So for the matching, you just take A and B to be just 1. And for the example I was mentioning, it was for the B, you take just B, and for the A, just 1. So we will not say much thing about it, we just, okay, you will see. So we want, if the sequence is not graphic, I want also to define my functional. So I define the XS as being the minimum of the sum from the way I to the way I prime over all sequence, and the sum of the Bj minus Bj prime over all sequence A prime and B prime, which are graphic. So such that there is a bipartite graph but with degree sequence A prime and B prime, and such that A prime I is less than AI and B prime J is less than Bj. Okay, so it's just the smallest number of edges that you need to lose to get a bipartite graph with this degree sequence, AB. Okay, and so you can define the same, the bipartite graph, you can define the same functional as being, when you look at the, for sequences which are not necessarily graphic, as being the minimum over all graphs, such that, which are maximal with, a bipartite graph G whose degree sequence reaches this minimum, this one, so which loses the fewest possible number of edges, is called maximal with capacity AB. So you can define the cost as being the minimum over all graphs which are maximal with capacity AB of the sum of the lengths. Okay, and it's reached for some optimal graph G star when the point set is finite. So how many? What's the size of this excess? So if the sequence A and B have some finite 2 plus epsilon moments, so you want at least that remember that the necessary condition that the sum of the AI has to be equal to the sum of the Bj. Okay? So if you want this balance equation to be satisfied when the AI and the Bj are RID, you want at least that M, the number of points from blue points, has to be equal to N, has to be roughly equal to N times the expected number of degrees from A divided by the expected number of points in B. Okay, so if you take n a fixed integral m, and m as being the integral part of n times expectation of B divided by expectation of A divided by expectation of B, you can prove using this the Erdős-Galai theorem that the number of edges that you lose is of order square root of n. So you don't lose, you lose square root of n points. And so, as David was saying, everything that you do with scaling argument tends to be quite trivial, so that's what we did. We fix this condition on the degree sequence. We take mutually independent random variables for the points with some distribution mu in a bounded domain. Of course, okay, I will say that later. And you call xk the first k points and yk the first k points of y. So n and m are related by m will always be the integral part of which is given by the balance equation. But the number of points, if you look at the expectation, we will prove in the next slide that it converges when you divide by 1 over minus p over d. So it just means that this expectation, if you take it's 1 over n times the expectation, the n power minus p over d, you put it upward, and you can write it's 1 over n over the sum over all points in x of the scale distance between xi and xj, where j runs over all points which are connected to point y in the optimal graph. Okay, so if you take expectation with respect to the position of x, you will have the integral where expectation given the first point is located at x. The expectation of the sum of the outgoing edge from 1 of the scale distance between this point which is at x and all the points which are connected to it. So this converge to a Poisson if with the proper assumption on mu. When you let n goes to infinity, it converges to a Poisson process with this parameter. So when you prove that this converge to something, it means that you are in the simplest case where your graph has a scaling limit on the Poisson process. And that's what we did. So it only works when P is strictly less than D over 2. So it means for the matching that it only works for D larger or equal to 3. That the expectation of the normalized expectation of the cost of the total length of my graph will scale like a constant times the integral of the function of a function f, where f is the absolutely continuous part of the measure mu. Okay, and beta depends only on the dimension and the law of P and the law of A and B. And you can remove the expectation and put in probability if gamma is large, as high enough, if A and B have high enough moments, and you can put almost surely if you have high enough moments. And you can also remove the fact that the assumption that mu has unbounded support if you add moments to. Okay, but just to connect this with what has been done, so this is kind of old-fashioned style of result. So 15 years ago, we discovered after that Jukic and Dorich made the case for the matching. The critical case, so when P is equal to D over 2 for the matching, so I was saying it's D equal to 2 and P equal to 1. There have been a fantastic amount of work, very nice work by Ashtai, Tomlosh and Tuznadi and Talagrand on the case where mu is simply the uniform measure on 0, 1 square, but it's much more complicated than what we did with Frank. In the stationary case for matching, so there have been a lot of recent work by Oroy, Perez and their co-authors, where they take X and Y as being an homogeneous Poisson processes, and then they are interested by, not necessarily by the minimal one, by the minimal, they have just looked at matchings, but you could define the same problem in the case of my graphs. They are interested by finding stationary allocations, stationary matchings on point processes. And when you have a single point process, so only X, and you want to build a graph with a given distribution, there have been some work which have motivated our result by Dayfron in 2009. So the upper bound is quite easy, so I will just go quite quickly. So you want to understand this. So the upper bound is quite easy, except that it doesn't satisfy the usual. If you open there is a nice books now on Euclidean combinatorial optimization, but this doesn't fit in the framework. But you still the main ideas can carry through if you do more with slightly more work. So the basic thing is for the upper bound is to look that if you divide your set of points into families, into subfamilies, so in X and in Y, an optimal graph, you can build it also as looking at the optimal graph in each of the subfamilies, and you will lose something which will be the number of edges that you have not been able to match. Okay? So you don't have an absolute bound on this, but you have a bound in expectation. That's what makes the problem not completely trivial. So what you do is you take a partition. You look at pk is a partition of the unit interval in 2 power k of d cubes, so cubes of length 2 minus k, and you apply this equality. You apply this inequality you iterate it by taking all partition from P0, so which is just the unit cube, to Pk. And at the end, by iterating this, you will get the sum, but the cost is less than the cost of each subset of points in each cube of your partition, plus some excess. And you can prove, you can prove that this will be summable, basically. So the lower bound is more tricky. The point is that to lower bound, there is you need to prove that the optimal graph is local in some sense. So you want to say that there is no too much edges which go far away. So, and to do that, there is a nice natural way, is just to change the metric and say that the distance between 2 points, okay, if the distance between 2 points will be the minimum of the Euclidean distance, and the distance between the 2 points, but you take the distance as being the minimum between x and the shortest point of x, the projection of x on the cube, okay, plus the distance of y and the projection of y on the cube, on the boundary of the cube, plus some cost epsilon. So it's very important here to put epsilon. So if you define this metric, since the distance here is less than the Euclidean distance, you can lower bound your cost by this. And then all the game is to try to bound the number of edges in the optimal graph of this that touch the boundary, so that really uses this part of the distance. And that's not so easy part. So I just want to conclude on to an application on minimal graphs, so which was motivated by a recent work of Holroyd in the case of matching. So so remember that the functional is the minimum of the whole graph which satisfy my degree constraints of the length, which is reached for some optimal graph when my point sets are finite. Okay, so it means that if I take any subgraph of the optimal graph, if I try to rewire the edges, okay, so if I try to look at the minimum of all graphs with the same vertex set than V of H and the same degree sequence that H, so if I take a subgraph of my optimal graph, so it could be that, so there are outgoing edges that I do not like, I do not consider. There is no way to rewire there is no way to rewire the edges so that to get a sum of lengths which is minimal by definition. Okay, so and Holroyd call this a minimal graph if for any subgraph, finite subgraph, you have this property that you cannot rewire your subgraph to get a sum of edge lengths lower. So the advantage of this notion is that it extends to infinite graph. So and such graphs are called P minimal. P because you have a P here. And as a consequence of our result, by a standard, there is from the result in the box from the result to stationary case of Poisson process, there is a limiting argument which is due to Holroyd and Perez, which is quite simple, but quite smart, which allows to say the thing that if you take consider two Poisson point process with intensity, the points are homogeneous Poisson point process, the intensity of the point of x is 1 and the intensity of the points in y is lambda, and you have marks attached, independent marks attached to all points which have distribution p for the points in x and q for the points in y, and the lambda and the expectation of a and b are related by this inequality, by the balance inequality. You can prove without much difficulty that if you are in the good regime where p is strictly less than d over 2, there exists a stationary bipartite random graph whose degree sequence is exactly this one, the degree sequence ak bk, which is p minimal. So the case of matchings is due to Holroyd. But this is not very deep. This cannot be a very deep result because it just depends on the upper bound, which is just part of the proof, which would be, I was hoping that the proof of the lower bound that we have which implies that the edges cannot go too far, will imply the unicity of this stationary bipartite random graph. But I've not been able to do that neither, so it's a bit frustrating part, but okay, that's what we have done so far with Frank on the topic. Okay, so thank you for your attention.
Questions?
For the first part, this triangle geometry is important, or you can do this for more?
So for the first part, what is important is strong symmetry. If you prefer squares, or it's fine. But what is important is that yeah, you have to have an invariance, an automorphism which goes from all bins to, and then it will work. I mean, you are in good shape so that it could work.
Since it's bit 12 to talk, maybe you would like to mention the conjecture of non-intersecting line.
There is a Yuval has a conjecture on this picture. So you take uniform n uniform points, blue points and red points on the. No, you take two Poisson processes on R2 of intensity 1, and you want to know if there exists a matching, a stationary matching of these 2 point processes, such that the edges do not, no pair of edge overlap. Okay? So if you could prove that the optimal matching scales if you could prove that there exists, you can define an optimal matching in 2 dimensions for Poisson processes, you would prove the conjecture, but I don't think it exists. So, can you build a matching such that stationary matching of 2 point process, such that no two pair of edges overlap?
The conjecture is that there is no such.
No such. Oh, okay, so there is no such.
I think I can probably say on behalf of the organisers that anyone who manages to prove that conjecture by the end of the workshop ought to be sure to let them know so they can write it out for the comments. But you have all lunch to think about it. Any other questions or conjectures? Okay, let's thank Charles.